Welcome to this explainer. Today, we're going to look up at the sky a little bit differently. We usually think of the atmosphere and weather as just random events, right? Things that just happen to us. But what if we completely reframe that? What if we look at the atmosphere not as random weather, but as a massive, invisible machine? Just like a car engine or a complex factory assembly line, this atmospheric machine has highly specific inputs, incredibly complex physical transfers, operational thresholds, and even failure points. Today we're diving into a very specific, rare, and highly destructive output of this machine, the Chilean tornado.
Think about a perfectly normal day. Have you ever just stood there watching a heavy rainstorm from your living room window, maybe checking your local forecast on your phone, and wondered exactly what unseen gears are turning in the hidden systems right above your roof? We see the rain pouring down, we feel the wind hitting the glass, but the high-stakes atmospheric engine driving the whole thing, it's mostly invisible to the naked eye. In this explainer, we're pulling back the curtain. We're going to completely deconstruct one of the most fascinating meteorological anomalies on Earth.
So here is the blueprint for our system analysis today. We'll start with the invisible atmospheric machine, move into the highly unique Chilean weather system, figure out exactly how the mesocyclone is built, define the thresholds of surface contact, look at verification and warning decisions, and finally wrap up with the limits of certainty. All right, let's jump right into part one, the invisible atmospheric machine. Okay, so let's look at the absolute foundational requirements for any severe storm system to operate. A tornado doesn't just magically appear out of thin air. It needs a parent thunderstorm, specifically a rotating supercell, which basically acts as the initial assembly plant. Now, for this plant to even be built, the atmosphere needs four very specific raw materials, known in the meteorology world by the acronym SLIM. We need shear, which is basically just wind changing speed or direction as you go higher up. We need lift to literally push the air upward. We need instability, which allows that rising air to just keep accelerating. And finally, moisture to fuel all that condensation. If this giant atmospheric machine is missing even a single one of these inputs, the severe thunderstorm simply fails to form. It's that simple. Moving right along to part two, the Chilean weather system. Now, while those slim ingredients are a universal recipe, the actual environment they're mixed in drastically changes the final product. And this is where things get really fascinating. There is a stark contrast between two entirely different atmospheric machines here. Over in the U.S. Great Plains, Tornado Alley, tornadoes are traditionally born from a pretty well-known model, explosive instability. You've got sizzling, moist air from the Gulf of Mexico, violently smashing into cold Canadian air and dry air off the Rockies. But down in south-central Chile, the machine runs on a much subtler recipe. Down there, we see what's called a high-shear, low-cape environment. Cape basically just means instability. So in Chile, the instability is actually pretty modest, but it's paired with incredibly deep, razor-sharp wind shear, typically driven by these massive extratropical cyclones rolling in from the Pacific. Plus, you have the Andes Mountains acting as this colossal physical wall, which totally modifies the low-level winds and intensifies that shear even further. It is a completely different operational setup. And because of that unique environment, it totally changes when this machine actually turns on. Because the Chilean system relies so heavily on that intense wind shear rather than just blistering summer heat, the peak tornado season in the heavily populated Central-South region doesn't happen in the summer at all. It actually happens during the cooler autumn and winter months, peaking right around May and June. To put that into perspective, further south in the Austral region, the threat actually does peak in the summer months of December and January, because that's when they get maximum humidity and solar heating. So the geography completely flips the script. Which brings us to part three. Building the mesocyclone. Okay, we've got our regional ingredients sorted out. Now let's map out the precise, localized physics of the storm itself and watch how this thing builds step by step. It all kicks off with that vertical wind shear we talked about, winds blowing at totally different speeds and directions at different altitudes. This actually creates invisible horizontal tubes of rolling air down in the lower atmosphere. Imagine an invisible rolling pin spinning in the sky. Next, the thunderstorm's powerful updraft, that lift and instability, grabs this rolling horizontal tube and literally tilts it completely upright. Once that rotation is flipped vertically, boom, we have successfully manufactured a mesocyclone. We now have a massive rotating column of air a few miles up, right inside the thunderstorm. But here's the catch. A mesocyclone, spinning a few miles up in the clouds, is not a tornado yet. As the storm matures, the heavy rainfall starts dragging cold air down with it, creating a mechanism called a rear flank downdraft, or RFD for short. This plunging cold air actually wraps right around the back of the mesocyclone. It physically pushes the rotating column downward and focuses it, squeezing it into a much tighter space. It's exactly like a figure skater pulling their arms in tight to spin faster. This vortex stretching process dramatically accelerates the wind speeds. That takes us directly into part 4, thresholds of surface contact. This is absolutely the most critical operational phase of the machine. It's the exact physical boundary where an invisible vortex crosses over and becomes a verified surface hazard. And we have to be super clear about the thresholds here because people misuse these terms all the time. A funnel cloud is a rotating condensation cloud extending down from the storm, but crucially, it has zero ground contact. It's just spinning up there in the air. A tornado, by strict meteorological definition, is a violently rotating column of air that is in contact with both the cloud base and the ground at the exact same time. If it is not touching the ground, it is not a tornado. In fact, hearing someone say tornado on the ground is technically completely redundant.
However, as powerful as it is, this machine is highly temperamental. There are so many system failure paths. Very often, you'll have highly favorable conditions that just totally fail to produce a tornado. Why? Well, sometimes that vortex stretching we talked about just isn't strong enough and the funnel never reaches the dirt. Sometimes the circulation down on the surface is just too weak to connect. Other times, the temperature of that rear flank downdraft is actually too cold. That creates a thermal mismatch that essentially chokes off the storm's updraft, just killing the engine entirely. And from our perspective on the ground, we also have verification failures. Powerful straight-line winds coming out of a storm can literally obliterate buildings, perfectly imitating tornado damage and causing totally false visual verifications by the people who see the aftermath.
But when the machine does not fail, the results are absolutely devastating. The ultimate physical evidence of this Chilean high-shear, low-cape system functioning flawlessly was the historic May 2019 outbreak. Over just a 24-hour window, this crazy series of powerful convective storms just swept through southern Chile. Let's look at the timeline. At 3 p.m. on May 30th, a vortex touched down in Quilelto. Less than 4 hours later, at 6:57 p.m., a highly destructive F2 tornado struck the city of Los Angeles, leaving massive infrastructure damage. Then, the very next day at 2 p.m., another F2 event violently tore through Talcahuano and Concepcion. This rapid back-to-back sequence proved without a shadow of a doubt that the Chilean atmospheric engine could absolutely manufacture catastrophic multi-vortex events.
Now for part 5, verification and warning decisions.
This leaves us with the final component of the system, us, the human observer. How do forecasters actually measure this chaotic machine in real time? Well, meteorologists are basically tasked with solving a deeply fragmented puzzle on the fly. Because tornadoes can be completely wrapped in rain or hidden in the dark, getting visual confirmation is incredibly hard. Forecasters have to rely on a massive blend of data inputs. They're constantly monitoring radar and satellite loops looking for those mesocyclones. They're tracking lightning data, analyzing surface and upper air observations, and consulting complex algorithmic models. But ultimately, because radar can't always see exactly what is happening right at the ground level, direct tornado verification heavily relies on human beings going out post-event and doing physical damage surveys on the ground.
And that reliance on human observation leads us to a genuinely staggering statistic. Get this. Prior to that massive 2019 outbreak, fewer than 12 tornadoes were officially confirmed in Chile over an entire century. 12. Now, does that mean the atmospheric machine was just broken or turned off for 100 years? Absolutely not. For decades, Chile's disaster preparedness was naturally obsessed with earthquakes, tsunamis, and volcanoes. Understandably so. But without standardized, aggressive meteorological damage surveys, countless narrow funnels that shredded remote rural areas simply went completely unrecorded. That sparse documentation basically created the illusion of an invisible threat.
Finally, let's talk about part 6, the limits of certainty.
Which brings us to our final point. We have to step back and honestly honor the scientific boundaries of atmospheric observation. Despite everything we've just mapped out, the shear, the lift, the RFD, the mesocyclone, we have to admit what we still just don't know. As it's often noted in meteorological literature, tornado genesis remains a complex process, and the intricacies of many of these formation mechanisms are still poorly understood. Even with the most advanced radar networks and supercomputer physics models on the planet, the exact microscopic triggers that cause one rotating supercell to drop a devastating tornado while an absolutely identical supercell right next to it drops nothing at all, it remains an incompletely understood process. The machine definitely still holds some of its secrets.
We've just seen how the perfect alignment of shear, humidity, and the mighty topography of the Andes can breed violent funnels under seemingly subdued, cool weather skies in Chile.
It really forces us to realize that the textbook models don't always apply everywhere perfectly. So I want to leave you with this thought. If this highly specific destructive mechanism has been quietly operating over South America for centuries, mostly unrecorded and unseen, what other invisible atmospheric engines are currently operating right above our heads, just waiting to be understood? Thank you so much for joining me for this explainer. Keep your eyes on the skies and never stop questioning the systems around you.